Today we're going to be talking about another transformation called a dilation. So yesterday we talked about translation. A translation is called a rigid transformation. And the reason it's called that is because a translation just changes the position of our shape, but it doesn't change the size. So when we do a translation, we just kind of shifted our figure around. We moved it horizontally and vertically, but we still ended up with a congruent shape, meaning it was the exact same as our original. In a dilation, this is a transformation that changes the size of a figure but not its shape. So an example of this would be if we had a triangle where, say, this was 3, this was 2, then we had another triangle where this was 4, and I wanted you to solve for x. A dilation ends up with similar figures, so something like this. So if I told you these two figures were similar, I could solve for x because I could say, well, 2 times 2 is 4, so therefore I had to multiply 3 by 2, so this side length would then have to be 6. So we're going to be doing dilations on the coordinate plane today. So we're going to be looking at how a dilation changes the ordered pairs, but also looking at the effect on the side lengths as well. So it changes the size of the figure, but not its shape. So it results in similar figures, meaning that they're the same shape, but not the same size. Also, the ratios of their side lengths have to be in proportion. So if I look here, I could say 2 over 4 is equal to 3 over 6. Those two ratios have to be in proportion to each other and they have to be equal to each other. When we're doing dilations, we're going to use something called a scale factor. So a scale factor is the number that describes the size change from an original figure to its image. So here, if I was dealing with these two, if this one was my original figure and this was the image, I could say that my scale factor is 2 because I multiplied 2 times 2 to get 4, 3 times 2 to get 6, so it's that number that I'm multiplying by in order to get to the image. So the first thing we're going to do here is we're going to graph a dilation. When doing this, you want to find the ordered pairs of the original vertices first. So I would look at A, and I can tell that A is at 1, 1. B is at 2, negative 1. And C is at 2, 0. So since they tell me that my scale factor is 2, that means that for my image, I'm going to multiply all of those ordered pairs, all of those coordinates by 2. So I'm going to take 1 times 2, which is 2. 1 times 2 is 2. B prime, I'd take 2 times 2, which is 4. Negative 1 times 2, which is negative 2. And then for C prime, 2 times 2 is 4, and 0 times 2 is 0. And now I can plot those points. So I'm going to go to 2, 2. So put my dot, and I'm going to label it A prime. It is very important that you label your points. For B prime, I'm going to go to 4, negative 2. Then C prime is at 4, 0. So now I got to draw my lines. Whoops. Try and make them a little straighter than what I'm doing here. And there's my image. So notice I went from triangle ABC to triangle A prime, B prime, C prime. Notice it got bigger. We call that type of dilation an enlargement because it's getting larger. Over here we can do the same thing. So I have a scale factor of 1/4. So I'm going to do the same thing and just take my original ordered pairs, but this time I'm going to multiply them by 1/4. So A is at 0, 4. B is at 4, negative 4. And C is at negative 4, negative 4. So then that means A prime, 0 times negative, or times 1/4 would be 0. 4 times 1/4 is 1. B prime, 4 times 1/4 is 1. Negative 4 times 1/4 is negative 1. And C prime, negative 4 times 1/4 is negative 1. Negative 4 times 1/4 is negative 1. So now I can plot my points. So I have 0, 1. So that's A prime. 1, negative 1, B prime. And then negative 1, negative 1, C prime. Notice that one got smaller. So we call that a reduction because we reduced the size. So one thing you can look at to decide if it makes sense how your shape ended up, or whether it's going to be an enlargement or a reduction, is the scale factor. So think, if I multiply any number by 1, it's going to stay the same. So if my scale factor is 1, I would just end up with the exact same figure. But if I'm going to multiply by a number greater than 1, my values are going to get greater, so that means it will be enlarged. It will be an enlargement dilation. If it's less than 1, it means my values are going to get smaller, so then it will result in a reduction. Another thing I would look at if I were you, so we looked at our coordinates at our ordered pairs, but let's also look at the relationship between our side lengths. So if I look between C and B here, I have 1, 2, 3, 4, 5, 6, 7, 8. And then it changed to 2. So think 8 times what value is going to give me 2? Well, 8 times 1/4 is 2, so then we did a good job there because that works. I could do the same thing here. So I have 1, 2, and then 1, 2, 3, 4. So I doubled in size there because it changed. It doubled the length there as well. So the next thing, we're going to look at it, and I want to know, is it going to be a reduction or is it going to be an enlargement? So I'm going from A to B here. So if I look at this first one, and if I look from A to B, I see that it got smaller, so I know it's going to be a reduction. But now I need to find the scale factor. I need to figure out what value did I multiply these ordered pairs by in order to get these. So I can look at ordered pairs if I want. So say I'm dealing with these two corners. So this first ordered pair, it started out at, that'd be -3, -3. And then for this ordered pair on B, that would be -1, -1. And really I could pick any corresponding vertices on these shapes if I wanted to. So the way I like to think about it is, okay, so I started with -3. I multiplied it by some value, which would be the scale factor, and then I got -1. So how could I figure out what that value would be? So at this point, I just have an equation. So I could divide both sides by -3. I can't divide that evenly, so I'm going to keep it as a fraction, but I can simplify out those negatives, so I would be left with a positive 1/3. So my scale factor there is a 1/3. I could also look at the side lengths. So here I start with 1, 2, 3, 4, 5, 6. And I'm going to multiply that by some value to get to this side length. So think about our similar figures. If I know that this is 6 and this is x, I had to multiply 6 by something, or I'll do y here. 6 by something to get here. Well, I know that that is 2. So to figure out what number I'm multiplying by, I could divide by 6. And so now 2 over 6, I can't do that evenly, but I can simplify it down to 1/3. So you can either use the ordered pairs and the coordinates there, or you can use the side lengths and that'll help you out. So if I look at this one, once again, it's a reduction because it started out big and then it ended up small. So now I need to find my scale factor. So I could either use this side or this side. Either one should work because remember, they're similar figures, so the ratios of the sides have to be equivalent. So if I do this, I went from 1, 2, 3, 4, 5, 6 times some value, and I got 2. So if I divide both sides by 6, x equals 1/3 again. So my scale factor is 1/3. Maybe you wanted to use the top. So here I have 1, 2, 3 on my original, multiplied by some value to get 1. I should still get 1/3 when I simplify here. And notice I do still get x equals 1/3. Some people really like to use the ordered pairs, so I'm going to use the top right corners here. So I went from -3, 3 to -1, 1. So I went from -3 times some value it's equal to -1. So if I divide by -3, then x equals 1/3. So all three ways there, notice I get the same value. If you look at this one, from A to B, my shape got bigger, so we would call that an enlargement. So here I'm going to use the top side, so now I need to find the scale factor. So I went from 2, multiplied it by some value, and I got 1, 2, 3, 4, 5. Oh, this one's not as nice. So if I divide both sides by 2, I have x equals 5/2. So if I look at that, initial reaction is, oh, that doesn't make sense. I got a fraction and it got bigger. But remember that that's equal to 2.5 or 2.5. So it is greater than 1. So therefore that does make sense. You could also use ordered pairs. So if I use these two, for the first one I'd have 0, 2. Next one I'd have 0, 5. So I'd end up with the same values there when I'm doing it. So 2 times some value equals 5. So if I divide both by 2, then I still end up with my 5/2 there, or 2.5. So my scale factor on this one is 2.5. So it is okay to have fractions or decimals as your scale factor. The next one we're going to do, this should look familiar because this is like our similar figures that we did at the beginning. But I want to know, is this a reduction or an enlargement? So if I look from A to B, it got larger, so it's an enlargement. But now I have to look at the information they give me to try find the values of the variables. So I know both 7 and 14. So remember, there's some, I need to write a ratio for with 8 and m, 10 and n, that's equal to the ratio of 7 to 14. So I can look at the relationship there, or I can look at the scale factor to figure out how did I go from 7 to 14. Well, I know that 7 times 2 is 14, so that means I had to do the same thing to 10 and the same thing to 8. So I know that m will be equal to 8 times 2, which is 16, and n will be equal to 10 times 2, whoops, which is 20. So if I checked that out, I'd have 7 to 14, which is equal to, hopefully, 8 to 16, which is hopefully equal to 10 to 20. So if I simplify those, I have 1/2 equals 1/2 equals 1/2. So since all of those ratios are equal, that means that I have the correct values there. Now we have to plot the points first before we can do the dilation. So A is at 0, 0. B is at -1, 2. And C is at 3, 3. So we need to draw the triangle. Struggling with straight lines today. And its image under a dilation of scale factor 2 on the same coordinate plane. So A prime, I'm going to change the color here. A prime, if A started at 0, 0, I'm going to take 0 times 2, which is 0. 0 times 2, which is 0. B prime, -1 times 2 is -2. 2 times 2 is 4. And then C prime, 3 times 2 is 6. And 3 times 2 is 6. So A prime will be at 0, 0, so I can just label right next to that since we already have a point. B prime I have -2, 4. Then C prime I have 6, 1, 2, 3, 4, 5, 6. And that'll be C prime. So now oops. Now I have my figure. So once again, you can double check your side links. So 1, 2, 3 was my original. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8 compared to 1, 2, 3, 4. So it looks like I'm good here and did a good job graphing that. Now the last thing I want you to look at is on this one. It says the screen on your old TV is 20 inches wide and 15 inches high. The screen on your new widescreen TV is 16 inches wide and 9 inches high. Is this screen on your new TV a dilation of the screen on your old TV? So remember, in order for it to be a dilation, they have to be similar figures. And that ratio has to be the same between our corresponding sides. So I want to know here, could I multiply 20 by something to get 16 and then 15 by the same thing to get 9? Or is my ratio of 20 to 16 equal to my ratio of 15 to 9? So I'm going to do it by simplifying. So I know that 4 goes into both of those, so I'd end up with 5/4. And I would end up with 5/3 here. Since that ratio is not the same, then it is no, because I cannot multiply them both by the same thing. I do not get equivalent ratios there, and they are not similar figures, so therefore it is not a dilation.